Alright, so we have this exercise, and what we really want to prove, and I'll just write it out in this way because I like this better, is that the closure of the union is equal to the union of the closures. And of course, we need finiteness here, but yeah, this will work. So we have two sets, and we want to prove that these sets are equal. So the general strategy is to prove by inclusion. So to prove that the union of the closures is contained in the closure of the unions, let's say X is in the union of the closures. This means that X must be in one of the closures. So if X is in the union of the EJ closures, then it's in one of the EI closures. Okay? And this holds for some I. Alright? So let C be a closed set such that C contains the union of the EJs. Because remember, what we're trying to prove here is we're taking X to be in the union of the closures, and we want to prove that X is in the closure of the unions. If we remember the definition of the closure of the unions, the closure of the unions, or the closure of a set, is the intersection of all closed sets which contain that set. So we take an arbitrary closed set C which contains this union, and we want to prove that X is in C. And alright, so I had messed this up, but now I figured it out. Okay, so let C be a closed set such that C contains the union of the EJs. What we want to prove is we want to prove that X is in C. Okay, so if C contains the union of the EJs, then in particular EI is contained in C. And since X is in EI closure, X is in C. Because EI closure is the intersection of all closed sets which contain the set EI. And C is a closed set which contains the set EI. And therefore, X is contained in the intersection of a whole bunch of sets, and one of these sets in the intersection is C. And so if you have an element which is contained in an intersection of a bunch of sets, then in particular that element is going to be contained in every single particular set that you're taking the intersection over. And so that tells us, because this set C is part of the intersection of closed sets that we're taking, we can conclude that X is in C. Okay. So for any closed set containing the union of the EJs, X is in that closed set. And remember, the closure of the union of the EJs is defined as the intersection of all closed sets which contain the union of the EJs. And for every such set, X, the element X, is in that set. And so when you take a whole bunch, if you take the intersection of these closed sets, you're taking the intersection of a whole bunch of sets, all of which contain X. And therefore, X is going to be in this intersection, i.e. X is going to be in the closure of the union of the EJs. Since this holds for all such C, we can conclude that X is in the union, the closure of the unions. And this holds for any x which is in the union of the closures, and thus we can conclude that the union of the closures is contained in the closure of the union. Alright, so that's one direction. And to prove that the union of the closures, to prove that the closure of the union is contained in the union of the closures, well, we certainly know that the union from 1 to n of Ej is contained in the union from 1 to n of the closure of Ej, because obviously, but every set is contained in its closure. So each EI is contained in EI closure, and this inclusion still holds true when we take a finite union. Well, when you take an arbitrary union. But in particular, this is true. Okay, so this is true. We know that the union from 1 to n of Ej is closed. And why is this? This is because we're taking a finite union of closed sets. And finite unions of closed sets are closed. And this is where you need finiteness. In fact, I seem to recall doing this exercise before. Maybe I did it somewhere else. But I believe the other direction holds for infinite unions. So an arbitrary union of closures is always contained in the closure of arbitrary unions. However, this direction, the union of closures being contained in the closure of union, only holds in the finite case, because you need this union of the closures, you need this to give you a finite. This needs to give you a closed set, and that doesn't necessarily happen if you're allowing for infinite unions. Alright, so this set is closed, and so if we take this inclusion that we have from the previous sentence and just take the closure of both sides, then we get the union from 1 to n of Ej closure is equal to the union from 1 to n of Ej closure. No, this is inclusion. Okay, but here we're taking the closure of a closed set, and so we just end up with the set that we started with, which is just the union from 1 to n of Ej. Alright, so this is what we want. We want the closure of the unions is contained in the union of the closures, and that's exactly what I've written here. So hence, now that we've got inclusion in both directions, we can conclude that the union of the closure of the unions is equal to the union of the closures, and that's what we wanted to prove, and so we're done with the exercise.